going to start a new chapter, okay? A new chapter, which is going to talk about vector functions. And 13.1, we're going to talk about vector function and scalar, okay? So what is a vector function, okay? Anybody have the idea? Well, a vector function is, remember in the past of function, the function value will be numbers, right? Real numbers. But in a vector function, the function that the output will be vector. So insert the number, instead output the number, it output a vector. Okay? So those are called vector function. And we're most interested in vector function, the output is going to be a three-dimensional vector. Okay, instead of the two-dimension, we're interested more into vector function, the output will be three-dimensional. Okay. Now, how do you know a vector function? A vector function, the output is a vector, so we put an R there, we put an M on top, indicate that the F it is a vector. And this vector is going to change as the time period change. So this vector here is going to change as this time period change. Okay. So the T here, as we call it from Map 110b, okay, this is actually a parameter. It's a parameter. Sometimes can refer to time. As different time, for different time, you have a different vector. Okay. So when you remember in 110b, we talk about parametric equation, we use T as a variable. Because a lot of time it's convenient to think about that as time. Okay? So that vector is going to change as the period change. So imagine at different times, the vector here is going to move. Okay. Now this vector here has three components. 1, 2, 3, like in three dimensions, right? So each one here is one. Those are component functions. Okay. So see the vector here, you use this label vector here to represent that. And you have three components. And each component over here, those functions here are real values. Okay? Real number, real number, real number. But this is the vector right there. Okay? So we use selected T to denote the independent variable because it will represent the most application of vector function. So T is actually we use it to, a lot of time we use to represent time. Just like if I say. Okay, now let's take a look at one example. In this example, we can see that we have a vector function. We have a vector function which is, it has three component function, right? 1, 2, 3. So the first component function, this is the ft, this is the gt, and this is the square root t, a three component function. So the domain of this vector function will consist of all values t that make each expression defined, right? Now look at the first component function. What's the domain for the first one? What was required for the first one? Only number, right? And the second one, we need when it's Ln. How does Ln look like? Well, Ln look like this. When we remember, I read for the function dense, right? It's a person here and the holder. Then the Ln is this one. Okay, it looks like this way. This is Ln of x. So this is the y-axis. Ln of x looks like this way. And as you can see, so if you have this picture in mind, you can actually help you remember the domain for the Ln right here. So when you have the Ln right here, then this quantity inside has to be what? And you see it is on the right side of this y-axis. So this quantity has to be strictly greater than 0. Yes, you got it. Okay. So we need this to be greater than 0. So we need 3 minus 2 to be greater than 0. Because Ln, for Ln, this quantity has to be greater than 0. Now, go to the last component. This is called t. So if it's an even root function, so t has to be non-negative. So it has to be greater than 0. Now we're going to combine the requirements. Right? So we require this to be greater than 0, we require this to be greater than 0. So for this one here, t has to be less than 2, right? So combine these two, then t is between 0 and 3, including 0 and 3. Okay, so that's the domain for the vector function. Any question? So that's how we find the domain of a vector function. Now we're going to talk about limits and continuity. So the limit of a vector function is defined by taking the limit of each component. Okay, so a vector function has 3 components. Then when you take the limit as this t approaching to a, all we do is we take the limit as t approaching to a of each component function. Right? That makes sense, right? When you try to take the limit as t approaching to a, you just take the limit of t approaching to a for each component function. Okay. Now, do you recall the definition for a function to be continuous at a? What was the definition in 110a? Say a function is continuous at a. A function is continuous at a even only if the limit of f of x as x approaching to a equals f of a. Right? So which means you can do a direct substitution. So if you can do a direct substitution and if limit equals f of a, then f of a is continuous at a. Okay. I'm sorry. If you okay. All right. So a vector function is continuous at a. Okay, continuous at a. You can do a direct substitution also. Let's try this, right? Okay. Where is that? He will be here only this week, okay? Because we can have someone to take care of him. Huh? This is great. Okay, I think degree and credit. Yeah, take care of credit. All right. Okay, he's going to take it. Okay. All right. So the limit. Okay. When you take this limit over here, okay. Then if you can move on, you can do a direct substitution, and then you get the function value, the vector value of this R of a. Then the vector function is continuous. You see the similarity between these two definitions? Yeah. So even only okay. So yes. Now we're going to talk about space curve. Okay. So space curve. It has space. It seems like fancy. Well, space curve is just a curve in space. Okay. So nothing too fancy. Okay. So there is a close connection between continuous vector function and space curve. Okay. I'm going to give you a picture here later, pretty soon. Okay. So suppose that, right? Remember, this is the first component, second component, and third component function, right? So what is that space curve? That space curve will consist of all those points x, y, z in space, where x equals the first component function, y equals the second component function, and z equals the third component function. Okay, as the t here value throughout the domain. Okay, like throughout the interval, it's called a space curve. And this big equation here, those are called parametric equation of the curve. The curve starts with the c, and multiply it. So put a c there for the curve. Okay. So we can think about c as being traced out by a moving particle. So think about the space curve, right? So you have x, y, z right here, right? And then you have this, then this point here, x, y, z, and then this vector, the position vector is from the origin to the point. And then as this point here moves, then the vector is going to move, right? And then as this one here, as this point here move, doesn't move. So the tip of this position vector is going to trace our space curve. So for example, if I do it this way, it might be a circle, right? And then if I do it this way, it might be a spiral, right? Okay. So we can consider the vector function. Okay, maybe I should give you a picture, then you can see better. Okay, here's a picture. Okay. So we have this point, the different x, y, z. Okay, this is the position vector of this point. And as you move this point here, then this position vector is going to move, right? And the tip of this is going to trace out this space curve right here. So imagine this vector, this position vector move, okay? The tip of it is going to trace out the space curve. Okay. All right. So let's go to this example. We're going to sketch this curve whose vector function, vector equation is given to be this, right? So the parametric equation for this space curve will be, well, it has this ijk, right? So this is the first one. The coefficient for this on here is the first component function. And then this is for the y, and this is for the z. So this is for x, y, and z. Now, whenever you see sine and cosine, and that will remind you of the trig identity, right? So the trig identity, that is the sine squared plus cosine squared equal to 1. Okay? So when you have something like this, you can say, well, I can make use of that identity. So I know that x squared plus y squared is equal to 1, right? So if x squared plus y squared equal to 1, so that means that for every point on this curve, x squared plus y squared equal to 1. So what does it mean? Let's think about it. So let's draw this in 3D. Okay, so this is an x, this is y, and this is z. Okay, so x squared plus y squared is always equal to 1. So on this xy plane, we have this x squared plus y squared equal to 1. Okay, this is for z equal to 0. But what about when z equal to, say, 1? We still have this x squared plus y squared equal to 1, right? And then this will be the space, this will be the curve, right? Okay, we still have that. So z here could be any, right? Okay. So we'll have x squared plus y squared equal to 1, okay? Will always happen, okay? So we know that the curve is now in this circular cylinder. So remember, this is the cylinder, okay? Remember, x squared plus y squared equal to 1. We don't think about it as just a circle. So in 3D space, it represents a cylinder. Now, so we know that. I thought it's equal to 2. Okay. And also, do you remember from Math 150, when you have cosine squared t plus sine squared t equal 1, and when x equals sine t, y equals sine t, when t goes from 0 to 2 pi, we actually take out a circle. That circle is going to, when t equal to 0, we end at this point. When t goes power 2 here, when t equal to pi, that here, t power 2, and then 2 pi go back to here. So what we have over here is we have x equal cosine t, y cosine t, right? This is x, this is y. Then as t goes from 0 to 2 pi, we're going to trace out this unit circle, starting at this point and ending at this point. And the direction that it traces out, it is counterclockwise. Okay? So cosine for that, sine for that, it is counterclockwise. Okay? So it actually has a direction. So it's starting from here, and then we move, right? And then trace our own circle. The t increase. It's in the counterclockwise direction. Okay. Okay, this point x, y, z lies directly above this point x, y, 0. Okay. Now imagine that if you have any point in space over here, right? So this one here, this point x, y, z, and if you project down to the xy plane, then the z component will be equal to 0, right? So when you project down to this xy plane, then this z over here is going to become 0. Okay, that is going to become 0. And we know that every one of this, when you project on the xy plane, will be this circle over here. Okay, so we see the projection, but how do we see the curve? Let's think about it. Okay, so the projection of the curve onto this xy plane has this, it's going to be a circle. It's going to be this circle right here. Counterclockwise, like this. Okay. And the curve, however, we still have t equal z equal to t. So our vector right here is what? So the first one here is, cosine t, this is sine t, and this is t, right? So from here we know that x squared plus 1 squared equal to 1. Okay, so we know that the projection of that is going to be the circle. It's going to be the circle for that. But what about this t over here? Well, this is d. D is equal to t. Okay. So which means that. So the d here, as the t increase, the d is going to increase. But the projection is still a circle. So think about this circular motion when the t here is increased, the d here is going to increase. So think about when you combine this circular motion and combine with the motion that's moving upward. What happens? When you move in a circle, but it's moving upward, right? So what kind of curve is that? So that will be a curve like this, okay? So it combines this circular motion with this upward motion, okay, when t increases. So you're going to have the projection like this. So it goes like this, and continue. Okay. So you combine this circular motion with this upward motion, you get something like a spiral. But the fancy name for this is called helix. Do you see helix somewhere before? Does it remind you of something? Does it remind you of what we see? Yeah? It's going to be what? Kind of like the DNA model. Yeah. So the DNA model right here is like the double helix. So you have this circular motion like this, and the other one like this. So the DNA model is like a double helix. Okay. Maybe I ask someone to. Okay, Matthew, could you
the torsion of the helix in the reservoir is familiar from its occurs in point experience. It also occurs in the model of DNA. In 1963, James Watson and Sergey Crick showed that the structure of the DNA also is that of two linked parallel helixes that are intertwined as a single group.
Okay, perfect. I have hard to translate this. The reborn Okay, anybody can answer?
The oxygen movement.
Oh, you're good, Kenny. Oh, good job. You're doing good. All right, nice. Okay. So, so in 1953, James Watson and Francis so that the structure of the DNA model is that of two main characters. Okay. Now we can remember this. The graph of the vector function is actually like this. You can think about. Okay. So it's a circular motion combined with the upward motion. Okay. Upward. Question? This is the favorite, right? Sometimes it might be that hard, right? How about we use computer to draw it, right? Okay, so let's go over this. So using computer to draw space curve. So sometimes it's difficult, right? Space curve is difficult to draw by hand. Okay, it's hard. Okay, some of them can be very complicated. So over here I have X to this, Y to this, Z to this, and then the space curve is something like that. Like something like this. And we have a name. This is called toroidal spiral. It's a toroidal spiral. So what's toroidal? Toroidal is relating to a donut. Okay, so this spiral here is nice on the donut. Okay, so that spiral nice on this curve. So you can use a computer generating graph. Okay. Now at the end, we can take a look at some graph right here. Another interesting curve is the, how do you say that? Okay, this one. It looks so random, right? What is it? Okay, might have some, we try to look it up. This might be, has some interesting application too, maybe. Okay, so X equal this, Y equal this, and this. It is very hard for you to graph this by hand, right? So the computer generating generating device will be better, right? So we can use that. Okay. Okay, now I'm gonna ask someone to read this. I'm gonna ask Melanie, could you read from here to here?
Something on a computer is used to draw space curve. Optical illusions make it difficult to get a good impression of what the curve really looks like. This is especially true for figure 8. The next example shows how to cope with this problem.
Perfect. Good job. Okay. So let's look at this example. Okay, Chester, could you read this example?
The computer that draws the curve expecting from R2 plus 2 squared to this curve is also called this distance in there.
All right, let's ask someone here. Okay. Benji, could you read this solution over here?
We start by using the computer to plot the parametric equations. The result is shown in, do you want to read that? X equals c, y equals c squared, z equals t cubed for t between -2 and 2. The result is shown in figure 9a, but it's hard to see the true nature of the curve in that graph alone.
Yeah, it's very hard to see. How does it look like, right? So even though you see that, still you don't see the whole picture, right? Okay. So what we could do that is we can put that in some box, in a box to display it. See, once you present curve that we just talked about, but if we make the coordinate, see, this is axis, this is the y-axis, okay? And we make a rectangular box and put the curve in this box. Now we have a better picture of this curve, okay? And we can see that the curve climbs from the lower corner of the box to the upper corner of the box, and it's going to be realized here, and it twists as it climbs, right? And then twist, and then climb, and end up over here. Okay. So this is, by the way, and you can also see the result by rotating the box. Okay, so we rotate the box, you can see one way. This is another view of the same curve. Okay, the twisted QE. Okay. Now, over here, we have three figures over here. When we look directly at the face of the box, okay, so if you look from above and look down, you see like this, it's a parabola. And if you look from maybe this way, it look like this, and if you look the other way, it look like this. Okay, so it's a different angle. Okay. So the first one here is the parabola, y equal x squared. This one here is g equal to x cubed, right? The g equal to x cubed, the other one. Okay, so so the curve is called a twisted cube. Twisted cube. I think it's because of this. Twisted cube. Now, another method of visualizing a space curve is to draw it on the surface. Right? The same one, right? The same twisted cube right here, right? The one that we just talked about, the twisted cube. We can actually draw it on the surface. Remember, y equal x squared is this cylinder. Y equal x squared is the cylinder. So we have y equal x squared on the xy plane, and then when z move, and you still have y equal x squared, y equal x squared. So imagine if y equal x squared is going to move, okay? And that's called a cylinder. Remember our definition of a cylinder, okay? So that's a cylinder, okay? And then we can eliminate the parameter from the first two parametric equation, x equal this, y equal this, we get this, right? So we know that it's a parabola. Okay. And then this one over here, so we get y equal x squared, so that means every point on the curve is going to lie on this y equal x squared. And then once you draw the cylinder and you put this curve here, and you can see that it actually lie on this cylinder. So it gives you a better idea how the curve looks like. Now, I want you to remember the helix, okay? The one that's important for you guys to remember is the helix, because we're going to do a lot of problem with the helix, okay? And what is the, do you guys remember what is the vector equation of helix? I said was looking over there, which is the point there, right? Yes, it's right here, okay? This one over here is for a helix. Cosine t, sin t, and t. Sometimes you can have two cosine t, two sin t, or this may be t over 2. But in general, it has cosine t, sin t here and the variable t in the third component. Then that will be a helix. Okay? So helix, remember this, okay? That's the helix. Okay. Now the helix over here, if you looking at that is not very good, right? However, if you put the cylinder, the x squared plus y squared equal 1 cylinder, okay, over there, and then you invert the helix on the surface of the cylinder, then it gets a better picture, right? It helps us understand it better, visualize it better, okay? So that's for the helix, okay? This one over here is the twisted cube. Again, with this one here, g equal to x cubed. That's okay. You see how it is. Okay. All right. Question? Does all those space curve interesting? So over here, we have seen the helix is used in the model of DNA. Okay. And read this paragraph. So I'm gonna ask. Okay, Yan, could you read from here to here?
Another notable example of a spacecraft in science is the trajectory of a positively charged particle in orthogonally oriented black magnetic to E and B.
Okay, very good. Okay. So I'm going to ask someone to read this. Wilson, could you read from here to here?
I think how the dimensional velocity given the quantum ability to map into a particle and figure the space curve through projection or the horizontal plane on the horizontal plane is the cycloid, or a curve whose projection is a line.
Trichoid. Trichoid. Okay, cycloid, trichoid. It seems like they want. Remember cycle? Do you guys remember cycle from map 110p? So in map 110p, when we talk about parametric equation, so when you try to parameterize the curve, remember the car wheel, okay? So when the car moves, then the wheel moves, then a point on the car wheel is going to trace out this cycloid. Okay. So here, so this, so we have this point over here. But when the wheel moves forward, then this is going to move, and it's going to trace out this cycle. So it looks like this. So that was what I'm going to do. Actually, cycle was Gary he was trying to, at one time he was suggesting maybe we can make the bridge in the shape of a cycle, right? Kind of imagine a bridge in the shape of a cycle, right? And then the car is going to be on it, and then the car will trace out a cycle on top of it. So the cycle of the cycle. Okay. So this is cycle, okay? And this is the vector equation for that, okay? For the projection on the horizontal cycle, and this is the cycle, okay? All right, so now today you have learned about vector equation and some of the space curve,